A single-line diagram SLD is a simplified representation of a three-phase power system. It's used extensively in power system engineering to analyze and design electrical networks, as well as for documentation purposes. What is a single-line diagram? In a three-phase power system, each power circuit consists of three conductors. A complete conventional diagram showing all the connections is impractical due to the complexity of power systems. Therefore, a single-line diagram is used, where three phases are denoted by a single conductor, assuming the power system is in a balanced steady state. Impedance and reactance diagrams. To analyze a power system under load conditions or upon the occurrence of a fault, it's essential to draw the per-phase equivalent circuit of the system using its one-line diagram. This equivalent circuit, known as the impedance diagram of the system, is drawn by combining the equivalent circuits for the various components shown in the one-line diagram. Representation of power system components on the single-line diagram. Each component is represented by its equivalent circuit. For instance, a generator is represented by an EMF in series with an impedance. Transformers and motors are represented by their equivalent circuits. A short line is represented by its series impedance. Medium and long lines are represented by nominal PI circuits, whereas very long lines are represented by equivalent PI circuits. Simplification in single-line diagrams. The resistance of a system is very small compared to its inductive reactance, so the resistance is often omitted when making fault calculations. Static loads I.e. The loads which do not involve rotating machines have little effect on the total line current during a fault and are usually omitted. Concept of a bus in single-line diagram. A bus in a single-line diagram is a node where one or more lines, transformers, generators, or loads are connected. Purpose of a single-line diagram. A single-line diagram is a valuable tool used in electrical engineering to represent the electrical system of a power distribution network in a simplified and easy-to-understand format. It provides a visual representation of the electrical components, their connections, and the flow of electrical energy throughout the system. The main purpose of a single-line diagram is to provide an overview of the power system, allowing engineers and technicians to understand the system's configuration, operation, and interconnections. It allows for quick identification of the main components such as generators, transformers, switchgear, and other important devices. The use of symbols and graphical representations in a single-line diagram makes it easier to interpret and analyze the power system. Different symbols are used to depict various components and their electrical characteristics, such as voltage levels, circuit breakers, disconnect switches, and protection devices. In addition, a single-line diagram serves as a reference document for maintenance and troubleshooting purposes. It helps identify potential faults or issues within the system and aids in the planning and implementation of system upgrades or modifications. It also provides a basis for conducting system studies and analyzing the electrical behavior of the network under different operating conditions or contingencies. Key elements of a single-line diagram. Generators. Transformers. Switchgear. Transmission lines. Distribution feeders. Protection devices. Components of a single-line diagram. A single-line diagram is a visual representation of a power system that shows the electrical connections and components in a simplified manner. It uses standardized symbols and lines to represent various pieces of equipment and their interconnections. A well-designed single-line diagram is crucial for understanding the overall configuration of a power system and for planning, designing, and operating it efficiently. Generators. The single-line diagram includes symbols for generators, which are the primary sources of electrical power in a power system. Generators can be represented by different symbols depending on their type, such as synchronous generators, induction generators, or even renewable energy sources like solar panels or wind turbines. Transformers. Transformers are another important component included in a single-line diagram. They are used to step up or step down the voltage levels between different parts of the power system. Transformers can be represented by symbols that indicate their primary and secondary windings, rated voltage, and tapping points. Switchgear and protection devices. Switchgear and protection devices, such as circuit breakers, relays, and fuses, are essential for the safe operation of a power system. These components are represented by symbols that indicate their positions in the circuit and their functions, such as protecting equipment from overloads or short circuits. Transmission and distribution lines. The single line diagram also includes symbols for transmission and distribution lines, which carry electrical power from the generators to the consumers. These symbols represent the conductor material, the line configuration overhead or underground, and the location of switches or breakers along the line. Loads and consumers. The single line diagram depicts the various types of loads and consumers connected to the power system. These can include residential, commercial, or industrial loads, and their symbols represent the type of load and the amount of power consumed. Other components. In addition to the above-mentioned components, a single line diagram may also include symbols for capacitors, reactors, meters, control panels, and other auxiliary devices that are necessary for the proper operation and control of the power system. A single line diagram is a graphical representation of a power system that portrays the various components and their interconnections. It allows engineers, operators, and maintenance personnel to understand the configuration of the power system and to make informed decisions regarding its operation and maintenance. Benefits of using single line diagrams. A single line diagram, also known as a one-line diagram, is a graphical representation of an electrical power system. It provides a simplified overview of the electrical components and their interconnections within the system. There are several benefits associated with using single-line diagrams in power systems. Easy visualization. Single-line diagrams offer a straightforward visual representation of the power system, making it easier for engineers and technicians to understand the system layout and component relationships. This simplification allows for quick identification of faults, potential issues, and troubleshooting activities. Documentation purpose. Single-line diagrams serve as a useful tool for documenting the power system. They provide a comprehensive and organized representation of electrical equipment, including transformers, generators, breakers, and other devices. This documentation is crucial for system design, maintenance, and upgrades, ensuring accurate records are available for future reference. Communication aid. Single-line diagrams are invaluable for effective communication among different stakeholders involved in the power system, such as engineers, operators, and maintenance personnel. The simplified graphical representation allows for better understanding and collaboration between parties, minimizing the risk of miscommunication and errors. System planning and analysis. Single-line diagrams form the basis for system planning and analysis. Engineers can utilize the diagram to assess the power system's capabilities, identify potential areas of improvement, and make informed decisions regarding system expansions or modifications. Emergency response. In the event of an electrical fault or emergency, a well-designed single-line diagram can be instrumental in streamlining the response process. Emergency personnel can quickly identify the affected components, isolate the fault, and restore power efficiently, minimizing downtime and ensuring the safety of personnel and equipment. In power engineering, a single-line diagram SLD, also sometimes called one-line diagram, is a simplest symbolic representation of an electric power system. A single line in the diagram typically corresponds to more than one physical conductor. In a direct current system, the line includes the supply and return paths. In a three-phase system, the line represents all three phases. The conductors are both supply and return due to the nature of the alternating current circuits. The one-line diagram has its largest application in power flow studies. Electrical elements such as circuit breakers, transformers, capacitors, busbars, and conductors are shown by standardized schematic symbols. Instead of representing each of three phases with a separate line or terminal, only one conductor is represented. Power systems are extremely complicated electrical networks that are geographically spread over very large areas. For the most part, they are also three-phase networks. Each power circuit consists of three conductors, and all devices such as generators, transformers, breakers, disconnects, etc. are installed in all three phases. In fact, the power systems are so complex that a complete conventional diagram showing all the connections is impractical. Yet, it is desirable that there is some concise way of communicating the basic arrangement of power system components. This is done by using a single-line diagram SLD. SLDs are also called one-line diagrams. For practicing electrical engineers and researchers, interpretation of single-line diagrams is equally important and required skill. First, you should know the common symbols used in an SLD. Without knowing the symbols, you can neither draw an SLD nor read it. You should know the common abbreviations used in an SLD. Let us see a list of few commonly used abbreviations. Electricity is usually generated in the ranges of 11 to 33 kV from different sources at generating station. After that, it is stepped up to either 132 kV, 220 kV, 500 kV, etc. by using step-up power transformer. Let's say 132 kV. After that, it is sent along transmission lines spread on hundreds to thousands of kilometers. It is received in a station called transmission substation, where it is stepped down to lower voltage levels. In the above example, it is stepped down to 33 kV. It is sent to another substation called distribution substation, where it is stepped down to 11 kV and then from 11 kV to 440 volts. Industrial consumers are supplied electricity at 11 kV and residential consumers at 440 volts or 220 volts.